Hello. Yeah. Okay. Yeah. Thanks. Thank you. Okay. So I just wanted to look at some of these numbers again. Whenever we are talking about standard model, can't make sense of standard model unless we are actually talking about numbers. So so let's look at, for instance, this hyperfine structure and see what it's like and what are the formulas that have to do with the splitting of the hyperfine structure. So let us see. So if you have non-relativistic hydrogen atom, then you have just the Bohr model, and then it's like spinless electron and proton, right? Then there's a first relativistic correction, where there is a term that goes as minus p to the 4 divided by 8, I think, or is it 3? 3 me cubed c squared. There's a relativistic correction because of this. And then after this, there is the fine structure constant, fine structure, and that is because of L dot S coupling, right? And then there is also the famous lamp shift for some of the levels, which is roughly at this scale. And then finally, so this is L dot S, and then after that you get the hyperfine structure, which is the coupling of the proton spin also, So that is where we were, and then we saw, or rather we need to see many things. We need to introduce the magnetic moment of the proton, which will be some gamma p times E by MPC SP, where this is what we need to compute or at least estimate in the Quark model. Then we have the splitting delta ENF, nth order, due to the hyperfine, which goes as m by mp alpha to the 4 mc squared gamma p by 2m cubed, and then it is plus minus 1 divided by f plus half L plus half. The plus and minus is according as f equals j plus minus half. Okay. So there are many things. There's the orbital angular momentum, which is j. Then there's a plus minus, no, this is the total angular momentum, which is L plus S, which is the orbital angular momentum plus the spin of the electron, and then that has to couple with plus minus half the spin of the proton. So this is the absolute total quantum number, total angular momentum, including proton spin. Yeah, MP, sorry. Yeah. And the Balmer formula, we all know, is En is minus alpha squared mc squared by 2n squared. Okay. So if you want to look at the 21 centimeter line, comes from I guess n equals 1, and for the triplet singlet splitting, so there L is equal to 0, and then there's a triplet singlet splitting. Why is it a triplet and a singlet? Because it's just half and half. L is equal to 0, so you have only the two spins, spin of the electron and spin of the proton. So these two spins can add up either to 0 or to 1. If it is 0, then it's the singlet. If it is 1, then it's the triplet. Okay. So this corresponds to F equals 1, and this corresponds to F equals 0. So you have a look at this and tell me what is it that you expect to see, that this energy level En is going to split into 2, and what is the relative magnitude of the split? One of them goes up and the other goes down, but there is a factor of how much difference between the two. Have a look at this and tell me what is the relative factor between the two. Okay, so it is 1 plus half, this is 3 by 2. Okay, this is half for both of them. So for the triplet, there's an additional 3 down here, whereas for the singlet there is no 3. Okay, so the relative factor between the two is 3. So that's why the singlet goes down much more, and then the total difference is 4. So if this is, so let's call this delta here. So this is delta is the increase, and this is 3 delta like this, and this difference is 4 delta. And there's a 3 that comes over here for this thing, and if you put it all together, then you get the following formula for the energy splitting. Where is the formula for the energy splitting? Epsilon for the energy splitting is 32 gamma p E1 squared. By the way, I have checked all these formulas, so I suggest you should also do this in order for you to figure out how much this is. So if this is the energy splitting between the two, I want you to compute lambda from this. Please take out your calculators, plug in all the numbers and so on, and then let's see how long it is going to take you to get this particular number. Okay. Take out your calculator. No notebook, no notes. How will you ever retain any of these if you're not going to write down notes? Yeah, but you should, and don't come late. This you don't have to. This number E1 you had better know by now. How much is it? 13.6 CV, huh? Exactly. It's also called a Rydberg, by the way. In some books, you will call it, this is for E1. By definition, is called a Rydberg, and this is 13.6 EV. Okay. Okay. Good. That you don't need to know. Everything else you can put in, and you quickly. Don't have to be quick. Take your time. Depends on how long you take. That much time we will spend. Okay, so let us see what are the various numbers that people have. So E1 we already said what it is, 13.6 EV. Gamma P is 2.79. Very good. Then NP is 938 times 10 to the 6 EV, right? C and all we don't need. So for lambda, we need to do the following. So I get epsilon equal to 5.8 7 times 10 to the minus 6 eV. Do you all get the same thing? That's what you get. Okay, so then for lambda, it's 2 pi h bar c divided by this energy. So that is 2 pi times 197. That's what I always remember this as. MeV femtometer. So I change this to minus 13 to get it in centimeter and divided by 5.87 times 10 to the minus 12 MeV, like that. Is good? Hmm? Isn't that amazing? So this is the famous 21 centimeter line, and it is used for all this, interstellar oxygen, hydrogen, and so on. It's totally amazing. And this was a prediction from long ago. Van der Hulst, he had predicted that there should be such a line observable. And what is it? Which part of the electromagnetic spectrum is it? 21 centimeters. It's microwave radiation. Okay. Now, so this is one of the very important lines in radio astronomy, which allows us to map interstellar hydrogen, molecular clouds, all kinds of things. Okay. So I'm going to ask you one more question now. Where do you think this number comes from? This 2.79, where does it come from? Okay. Now, if you people believe that, what is proton made of? Proton. And neutron? 2 downforce, you're sure, 100%. So this number 2.79 should be somehow related to the fact that the proton is made up of constituents. Otherwise, it would be just a, it would be like a Dirac particle. It would just be, there's no gamma p, it should just be equal to 1. So here's the first sign that a proton and neutron are composite. Okay, but by now we have all convinced ourselves that the quark model is very good, and if it is good, it had also better be reasonably good quantitatively. And if you're so sure that it is made up of 2 u quarks and a d quark, then you should say, if I knew the individual magnetic moments of the quarks, then I better know how to build up a proton and a neutron out of that. Except there's a problem. Each one of these quarks is a spin half particle. So you have to combine these 3 spin half particles in order to get a spin half particle, which is allowed by the rules of quantum mechanics and angular momentum addition and all these things. Okay, so you have to do some extra work, unless unlike, let's say, the delta. Delta is very simple because delta is 3 halves. All the quarks are pointing up, spins are pointing up. Therefore, you just add up their individual magnetic moments, and there's nothing more to be done. Whereas here, because of the fact that you have to symmetrize and anti-symmetrize properly, then the formula is a little more complicated. Okay, but it can still be done in the constituent quark model. And let's say in this constituent quark model, experimentally measured. So this, after symmetrizing and anti-symmetrizing in the spins and the colors and in the flavors, etc., you get an answer that looks like this, which is 4 times mu of the u, 4 times the magnetic moment of the up quark minus mu d. Okay, this is a simple calculation. It has algebra. It's there in Griffiths, and you can follow it. There's no point in doing this in class. Now, if you say that a proton and neutron are the same except for the swap of the u and d quarks, then please tell me what is the mu of the neutron is 1 by 3 times 4 mu d minus mu u. You guys are my favorite students, you know, because you help me with all this very complicated ideas. Now, let us say we don't know what this is, that there is some constant k, let me call it k by 3, and we know that the magnetic moment is proportional to the electric charge. Okay, so I've pulled out everything except for the factor of the electric charge, and so what should I put over here? 2 by 3 minus, and here minus 1 by 3. Thank you. And here what should I get? This is 4 times minus 1 by 3 minus 2 by 3. Okay, now please calculate these for me, what these factors are. 8, 9, right? Is just k, and this thing here minus 2k by 3. Okay, yes, because if you look at the definition of the of a magnetic moment of any part of a Dirac particle, it's proportional to the charge of the Dirac particle. Now we are pretending that the u and the d are Dirac particles. They are in there, they are Dirac particles, and all the other interactions and so on, or the gluons, everything is lumped into this k. Okay, so since you know that for a Dirac particle it has to be proportional to the charge, all the unknown stuff is pushed into the k. This is okay. So now you please predict for me. You asked me what is mu p. You said mu p was 2.79. Use this formula and predict for me what is mu n. Use this formula and tell me what is mu n. Minus 1.86 prediction, and the actual experiment is minus no 1.91, I think. Have a look, Google it. Minus 1.91 experimentally. So this supports the idea that this is correct. Okay, this k also you can estimate. K can be estimated in the constituent quark model. The constituent quark model. And it comes out okay, but you have some parameters that you have to fit, and then you have to input the mass of the proton and so on. So it's not really a prediction. Okay, but this is very good, no? I mean, here we are talking about 21 centimeter line, which is something from interstellar gas, and that has the same value of gamma p that I have in my constituent quark model. Think about it, you know, how astonishing it is that you're able to use all these predictions in order to say something about. So you're using some information from celestial observations, and then you are able to fit something on terrestrial scales, or you use something from terrestrial scales that you're able to say something about that. Now, in my opinion, this is pretty amazing, but probably you people are not impressed by all this anymore. You're the era that does Instagram and Snapchat and so on, while people of my age had with paper and pencil. So different things impress different generations, I guess. Okay, so that was the hyperfine structure. Okay. Now I want to tell you a little bit about everything that we have done in this course so far has been just drawing tree level diagrams. Okay, we are talking about vertices, strength of the vertex, whether it's weak or strong, or electromagnetic. Yeah. No, it's a magnetic moment. Magnetic moment. Yeah. There's no electric dipole moment of any fundamental particles. So I want to, what was I saying? Yeah, so we also have to deal with loops. Now we know that we live in a quantum mechanical world, so if you just write down the Lagrangian in terms of fields, and you look at the constants of the coupling constants of the Lagrangian, which is very useful for practical calculations, especially in weak interactions or QED. But we know that that's not the end of the story, because we live in a quantum world, and a quantum world necessarily means the existence of loops. We know that a full theory is not just loops, but it's a full non-perturbative solution. You may or may not have it, but certainly perturbation theory you should do. And of course all this is presented as some kind of a religious experience, because it's quite difficult, renormalization and so on. You know, we are accustomed to these words, that they are very complicated, and we feel that there is some mystical and spiritual element to it, but it's not. It is just something that you're forced to do because your theory takes you in that direction. So let me again go to QED, which is the simplest theory, where L is a function of the fields psi. A mu has only two parameters, E and ME, nothing else. This is L. Okay, and there are rules which allow you to do rules, Feynman rules, which tell you that, look, there are propagators like this, and then there is a fundamental vertex like this. Okay, so these are read off from the Lagrangian, But then we also said that Gaussian integration, etc., tells you how to get the Feynman expansion. So at one loop, there are three diagrams that you need to consider. And what are the three? You all know what these are. And one of them is called this. This is called the vacuum polarization. Then there's another one like this, which is called self energy. And then there is another one, this, which is called the vertex correction. Okay, we know how to handle these things, we know how to regularize this, etc., and to be able to start dealing with the renormalization of QED, which we know is renormalizable in 4 dimensions, because you can compute the dimension of the coupling constant E gamma mu, and you know that it's dimensionless and so on. Now again, this is where it's presented as a spiritual experience, but then you have to ask, what are the actual physical consequences of such a thing? Okay. So this, you will agree with me that this leads to G minus 2 of any of the leptons, which at leading order is alpha by 2 pi. Okay, so this we have to somehow convince ourselves that in standard model we know how to pull out something like this. What about vacuum polarization? Vacuum polarization is sure to show up in, let's say, E plus E minus 2, mu plus mu minus, E plus E minus to mu plus mu minus, where there will be a contribution of vacuum polarization like this. Okay. Other diagrams of this kind actually will not be important. For instance, you'll have something like this over here, okay? Or you may have this, but we don't actually do them because these are not one particle irreducible. So that's the reason why these things don't. So this is an external, it's an external line renormalization, so we disregard that in this particular process, we disregard this in this particular process, and this is the thing that will show up for vacuum polarization. So this will show up in vacuum polarization. What about this? Where is this thing going to show up? Okay. So this, there's a mysterious remark in books which say that this is actually arising from the quantization of the electromagnetic field itself. And I was wondering, what does that really mean? It means that you have to consider the possibility of emission of quanta which are then reabsorbed in the self-energy diagram, which I just said does not show up here. It is not important over here, but it's important in some other context. And what is the context in which that at one loop, where where you're addressing an external leg, it's somehow not that significant. Again, these are all technical reasons, but I'm just motivating it. Actually, my motivation is to motivate the self energy and where you think it might be visible. Okay, which process or which observable? So that's my question. And everything that I've talked about so far has been in atomic systems. Okay, I talked about fine splitting, hyperfine, and I mentioned one other context, and that's the context in which I think that this will show up. And what is that context? It's the lamp shift. Okay, and where does the lamp shift appear, and what shifts? When you say that there's a shift, what kind of shift? Lamb is not the animal, but it's the person who discovered this in spectroscopic experiments, Willis Lamb. So his Nobel Prize was shared with the guy who measured this G-2, the electron, Polycarp Kupch. So those are the two guys who shared the Nobel Prize for checking fundamental predictions of QED in experimental systems. Okay, so that'll show up in your G-2, and the number they measure in 1948 or so is incredible. Okay, they have errors, but the central value sits on top of this alpha by 2 pi, which was predicted by Schwinger. You should read Schwinger's paper also. Read Schwinger and Polycarp Kupch. Schwinger's paper is like half a page. Okay, and he has his formula, and after he passed away, they put those symbols on his gravestone. Okay. Well, some human interest stories, but it's so boring otherwise. Physics so dry. Okay. Of course, it's very difficult to calculate. So I said lamp shift, and it's a shift in certain spectroscopic lines. And which spectroscopic lines are those? So this actually, this shows up before hyperfine splitting. Okay, before hyperfine splitting. So this actually removes the degeneracy between 2s, what, 2s half and 2p half. Is that right? Yes, thanks. 2s half and 2p half. So this means that it's the energy that you need to excite the electron that's in the 2s half and free it, and take it from 2p half and to free it, but there's a small energy difference between the two. So this means that you actually have to solve the bound state problem where the electron is not a free electron, but the electron is actually sitting inside the hydrogen atom. Okay, now we know that it's impossible to solve relativistic bound state problems. Even today in the year 2025, we cannot solve relativistic bound state problems. So how to do this calculation? So Bethe actually did this using very clever non-relativistic arguments, and he got a beautiful answer. And this result of Lamb was announced at a conference somewhere in New York, in the state of New York. And Bethe was going back home, and on the train, there's a famous story of in the train ride how he did the calculation, got the answer right, without any books, without any Mathematica, nothing. That was a different era. That's because he knew all these numbers inside out, totally cold. He knew them. Why did he know them? Because he was also worked on the Manhattan Project, and they had to calculate all these cross sections. Otherwise you'll end up blowing up your lab rather than someone else that you want to blow up. So, and also later he put his knowledge to compute the nuclear processes in a certain star. Which star? Which star did he calculate? Do you know any stars? Name of one star. Non-neutron star, the sun, for God's sake. So he calculated all the energy processes of the sun, and he knew all these nuclear cross sections. He just start in the morning, keep on calculating cross sections till he went home. Okay, he got the answer right, and that's how even today the basic papers on all the solar physics is done by Bethe, all those nuclear cross sections. So that's how he knew these things, and I'll now give you the answer for what is the Lamb shift, and I'm going to ask you to compute these numbers for yourself or on the blackboard. So it's 8 by 3 pi alpha cubed by, please see his paper also. Okay, it's a 2-page paper in Physical Review, volume 72, to see what that era was like. Times the Rydberg times natural logarithm of k divided by the average energy of all the states delta L0 like this. Okay, so this is the formula. So this is for the S state E minus ES. He got this from a colleague, 17.8 Rydberg, and so we know what this answer is. So this formula is for the energy splitting, delta E. So this is the energy splitting. Yeah, so K is taken to be the mass of the electron. See, this was not a full calculation. It was an order of magnitude estimate driven by various physical arguments, and n here is equal to 2. N is equal to 2. So please get the energy and get me the nu, which is E, delta E rather. So this is delta E with L equals 0 and N equals 2. Delta E and divided by H, and get me what the number here is. So this correction is only for the L equals 0. So we have two states over here, L and E. Okay, so it only lifts one of them but doesn't lift the other. Yes, yes. There are other corrections also to the P, but they are all subleading. So at least within the approximation of Bethe, this is the answer. Okay, so let's get this. So we know what H is. So H is 2 pi times 6.5 times 10 to the minus 16 eV second. Okay. You get it? Got it? Hmm? Yes, roughly. But what is the actual answer you get? Correct. So, so Leo here gives us the answer of 1.05. No, 1.04. Is it? 0.05 gigahertz, which is often given as 1050 megahertz, and this is a pretty amazing thing. Okay, and the actual experimental number is very close. It's 1057 or so. So these are all numbers that you should know. If somebody asks you if renormalization is a spiritual experience, you should say no. You should go to the atomic physics and say that it's a demonstrable effect where it's. So how did Bethe actually argue that this should be the case? So what happens is you have the electron over here, it's sitting in one of the bound states, which emits a photon, and then it reabsorbs it. Okay, but if you have to do it in second order perturbation theory, what do you have to do in second order perturbation theory? You get a sum over all intermediate states divided by an energy denominator. Okay, and the sum over all intermediate states means what in this particular case? What is the Hilbert space of this hydrogen? There's also a sector of the Hilbert space which has to do with the photons, okay, with the virtual photon that is emitted. So that sector of the Hilbert space is actually only transverse photons, but doesn't matter for the moment. Anyway, you have energy conservation, all these things are taken into account, but it's. So what is the sum over intermediate states? It's actually a resolution of the identity that you do, right? In operator theory, you would do all these things. So here, what is the spectrum? What is the spectrum of this system? Non-relativistic hydrogen atom. What's the spectrum? Energy levels and after 13.6 eV, what happens? You get scattering states. You get a continuum. Okay. So then you have the free electron, right? So the Hilbert space of the system is the discrete as well as the continuum. So Bethe's way of looking at this was to say that this actual mass correction is the difference between computing this set of intermediate states over the entire thing and over the continuum. So if you take the difference between those two, he argued that it must be these contribution you get to the sum from the discrete part. Okay, and when you do that, that is where you get this particular logarithm from with this particular energy average. It's a very ingenious thing, and the only place I know where it is done in a nice accessible way, 3 pages of algebra, is in the book of Mandel and Shaw. It's very good. And someday when you are stuck somewhere, you know, the internet is broken down and then you can't watch Netflix, then you take out Mandel and Shaw, your iPad or whatever, or Kindle, and then you go through those 3 pages. It's a very nice derivation. Okay. By the way, there's also a contribution to this energy splitting due to vacuum polarization also, which predates this but is numerically small, and that's called the U-link term. U-E-H-L-I-N-G. U-link term also gives a contribution, but it's very small, and let me give you the expression for that. The reason for doing all this is nobody talks about these things. When you talk about standard model, they're only talking about very, very high falutin things. Nobody talks about this basic stuff. Where is it gone now? Oh, here it is. U-link term here is minus 8 alpha cubed divided by 15 pi n cubed times Rydberg times delta L0. Now, when I say it is small, I want you to compute and tell me what it is. How small is it really? And why do you think the lamp contribution is much higher because this is kind of looking like the same thing. Okay, calculate this and tell me. So Yuling, also for 2s obviously. Vacuum polarization. It's the bound state vacuum polarization. Somehow, I mean, it's an effective thing, and but I don't know exactly what is the line that's getting corrected. It's probably the static Coulomb interaction between the electron and the proton it receives. It's a good question. You should check, find out, and let us know. Yeah. 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 Exactly. Excellent. Yeah. So with a minus sign, minus 27 megahertz, right? You see, so these things should fix in your mind once and for all. What are the various energy scales? What is the spectroscopic line, etc., etc. Okay. And this is an introduction to something very important. What is the important thing that I have done today that I have not done in the previous 10 meetings? What is it? Of course, most of you haven't attended all 10, but you should try to guess. No, that we've been talking about. But there's one crucial thing that I've done today, which I haven't done in any previous class, which is I've looked at loops, okay? Giving you a gentle introduction to loops. And we have to do it. So when you talk about a quantum field theory, standard models of quantum field theory, you have to deal with loops, okay? In contrast to, say, QFT courses where you go deep into the theory of renormalization and all, my approach is to just do that part of renormalization which allows you to link it to observables. And what in the world can be simpler observables than, say, spectroscopic lines, okay? And to prove that these things are actually, things that you can feel and see in the laboratory. Okay? These things are now seen in tabletop experiments. They were measured in 1948, so you can imagine. You didn't have LHC or any of these things in those days, as far as I know. Okay, so that's that. What else did I want to say? I think I wanted to say a lot of things that I can't remember anymore. Want to say a few words about some of the things we did the other day, a bit more in detail. For instance, I had mentioned Quarkonia, right? Quarkonia. And we basically mentioned two systems, Charmonia and Bottomonia. And these are bound states of CC bar, PP bar. So let me ask you a question. Where do you think you may be able to produce something like Charmonium and Bottomonium? What kind of experiments do you think you might be able to produce it, and how? What would you do in order to do such a thing? Okay, it's pair production after all. Give me an example of pair production. E plus E minus going to mu plus mu minus. And this can happen only if the central mass energy in the E plus E minus collision is more than twice the mass of the muon, right? So similarly, you think you can produce E plus E minus to CC bar if the central mass energy is enough to produce CC bar, right? So that's kind of common sense. But this CC bar is going to be produced not as quarks, but it's going to be produced as a bound state, okay? and if you have two spin half particles, then they bind to give a composite state which also carries other quantum numbers. For instance, if you produce E plus E minus collisions at low energies, you can produce a pi plus pi minus pair in the final state. Okay, of course you're producing all kinds of quarks and so on, but what you see in the final state are pi plus pi minus pairs. But in the intermediate state, you produce something known as a rho meson. What is a rho meson? Rho meson. Okay. Anybody? Now you know that there's a pseudoscalar octet, right? Ions, kaons, and so on. So it's a vector particle. That means it's also a QQ bar bound state, but with angular momentum of 1. It's a vector particle, so it has to transform as a Lorentz vector. Therefore, it must carry spin 1. So if you have E plus E minus, then you'll see a big bump in the cross section when you cross the energy of the rho, which is a vector resonance, which is also a bound state of quarks. And then this vector resonance, which is 770 MeV, breaks up into pi plus pi minus, which adds up to only 280 MeV. The rest of the energy is carried away as kinetic energy by the pi plus pi minus pair. So why is this thing 770 MeV? Why is it so heavy compared to two pions? Why? You have to think about these things, no? When you have numbers, you have to ask, why is it like that? The answer is that it's a chromomagnetic energy of trying to line up two quark spins. And then that energy is spontaneously released by the emission of pi plus pi minus. Similarly, if you produce CC bar in a bound state with the correct quantum numbers as a vector, then part of the energy that you have has to go into this magnetic energy. But since the charm quark itself is so heavy, the magnetic energy is small compared to the mass of the C quark, okay, or the CC bar pair. So that's why you don't need the energy difference is not so high in CC bar and BB bar as it is in the case of, let us say, the light quarks and the rho meson. What about SS bar? Supposing you want to produce two S quarks and two mesons, E plus E minus to K plus K minus, then you need some intermediate state which is a bound state of SS bar with, you know, spins lined up and so on. What is that particle called? Just as you have the pseudoscalar octet, there's also the vector octet. And when you look at that vector octet, look at the vector octet and tell me which one of them is the resonance for SS bar production. I'm trying to make this course and this discussion something that is a living organism, you know, not just a bunch of dead facts sitting in books. You have to think about each one of these things as actually meaning something, okay? Not something that you just memorize from the textbook. Of course, if you want to do that too, you can do that. It is a free world after all. Okay? Did you find something? Not CC bar. First, I'm asking about SS bar. Look at the vector on it. So it's this phi, the phi resonance, which weighs 1020 MeV. 1020 MeV is an SS bar. That's why it's sitting in the middle. And what is the mass of a kaon? Kaon, quick. By now we should know all this. Oh, twice that is 980. So 1020 is more. Then that is why when the phi resonance is produced, it can decay into a KK bar pair. Okay. So just as the rho is a resonance for pi plus pi minus channel, the phi is a resonance for the KK bar channel. Okay. So if you go in this way sequentially, then you look for one more resonance for CC bar. Then you look for another resonance for BB bar. What are those resonances? These are very famous resonances. I think this is actually the 50th anniversary of the CC bar resonance, which of course is also a Nobel Prize. Of course, all you have to do is find a resonance, you'll get a Nobel Prize. No longer, but in those days. It's called a J psi. So in CC bar, if you E plus E minus produces a J psi, which then decays. And E plus E minus goes to something called an epsilon. Why is it called J psi? Because one group called it J and the other group called it psi. They were fierce competitors, and because they hated each other, finally you had to name it after both of them. Okay? So we have very objective, concrete reasons for why particles are named the way they are. Okay? So people have to hate each other in order for a particle to get a name. So this is called an epsilon, and this is called a J psi. Okay? And these particles, as we already said, so this has the correct, so it has a vector resonance, and let's see, where did I write down? Did I write down or did I lose all my notes? Shit. So this is the lowest lying vector resonances. There are other vector resonances also. So why is that? Why can you have other vector resonances? Well, you know, you have a CC bar and you're orbiting around each other like that. So this is the ground state of this orbit. You can have a higher orbital motion also, and a higher orbital motion also. So that's the reason why you can have particles which have the same angular quantum number but different principal quantum numbers, because it behaves like a hydrogenic system. Okay? It's only the lowest lying states that behave like they're hydrogenic, because the potential at short distances is Coulomb-like. So at the bottom of the Coulomb potential near the origin, you can have hydrogen-like states. But I already said that quarks are confining. So if you try to pull these guys apart, then there has to be another component to the potential which is confining. Okay, and we mentioned this already. So for instance, we wrote down V of r is minus 4 by 3 alpha s h bar c by r plus f naught r, and we said that this comes from the color indices, and this f naught is called we gave a name for this, it's called the string tension, and it's of the order of 900 MeV. So it's a very strong confining spring-like potential that you have for this thing. This J psi has a quantum numbers of 1, 3s. So here, as was the case with hydrogen, after hyperfine splitting, there is a total angular quantum number. Okay, it's a total angular quantum number, which no longer distinguishes between the individual spins and the angular momentum, and that is what is sitting over here. Okay, so that is what sits over here. So actually you should read a little bit about exactly what is the meaning of the spectroscopic notation. So this J psi is such a state where it must have the correct quantum numbers in order to couple with the photon. Okay, so you have E plus E minus, which produces a virtual photon, which then produces a J psi, which then produces decay products. So this is the CC bar pair over here, CC bar pair. And it's very funny that this is a very long-lived particle, and there's a empirical rule which, so this decays into 3 pions, which looks like this. So there's an internal quark line that looks like this, and this produces 3 pions like this. One, this one is here only like this, and this produces 3 pions. So here is a pi, here's another pi. So it's a very long-lived state. So these are all gluons, long-lived, because it requires 3 gluons in order for this process to proceed, because energetically it cannot decay into 2 charmed mesons. There is another heavier one which looks like this, where the CC bar pair produces something like this, where it produces a D plus and a D minus. What are these D mesons? By now you should know what is a D meson. A D meson is like a K meson, except that the S is replaced by C. Okay. What are B mesons? Capital B mesons, where the S quark is replaced by a V quark. Okay. So this is the nomenclature for these things. So this is for heavier size states. States allowed. There's a famous empirical rule which says that such things are possible. It's called the OZI rule, Okubo Zweig Izuka rule. It's an empirical rule. To date, we don't understand its origins really, which gives you some kind of hierarchy of when such things are possible and when such things are possible. So somebody tells you that standard model is all verified and all these things. It means that we know how to tackle enormous data like this, which are collected at various laboratories across the world, various lifetimes, various decays, various branching rules. That's what is meant by standard model. Okay, it's not just some small book where the author says standard model has now been verified in all experiments. So it means that every one of these things has to be dealt with. So similarly, there is a system for bottomonium. There is a system of epsilon states. And just as you have an opening up of channels like this, there is a state known as epsilon 4s, which can produce BB bar pairs. BB bar pairs. And the Bell experiment in all these things, they collide E plus and E minus at such energies. Okay, this Bell experiment, etc. So every term that you run across whenever you're reading, say, a book or a brochure on these experiments, and they say epsilon 4s, it means this 4 is the 4th principal quantum number in that excitation. Okay, so there's an epsilon 1, epsilon 2, epsilon 3, epsilon 4, and only when you read epsilon 4 you have enough energy to produce B plus B minus. Otherwise the epsilon and so on, the lower epsilons, will break up into pions, and it could break up into SS bar pairs or and so on. I mean, there are various branching ratios for each one of these processes that you have to deal with. I am actually recovering from a pretty bad cold and cough, so I'm a little tired. So I don't want to continue the lecture now, but let's take some time to discuss many of the things, and then I will do the next topic in the coming classes. Okay. And for your projects, what we will do is each project will get 1.5 hours during the class time. So when you are presenting your project, it's like you're going to be the teacher of that particular topic to the entire class. Okay. And so we will do it as part of the classroom itself. It's not like I need a separate hour where you people are going to give your, no. So supposing we want neutrinos, whoever has got neutrinos as their topic, they'll get 1.5 hours to teach the rest of the class about neutrinos. Okay. It's just that I sit there and you stand up here. So 6 class hours, or 6 times 1.5 hours will be used, and this will be in the month of April, I guess. I think we may have 6 classes in April. Maybe we won't have 6, in which case we will start the end of March. Okay. So that's what we're going to do for this particular thing. And the order in which we will do it, we will draw lots like we did previous time, so that some people can't say, oh, I didn't have enough time, that guy had too much time. Not like that. So we will just view this as part of your learning and start right now. Don't wait till you're reaching that date to actually sit down with your topic and with your presentation. Start right now. Okay. Any questions? The next thing that I'm going to do in the next class is to look at this other vacuum polarity, this other QED one loop diagrams, both for the G-2 as well as the vacuum polarization. Of course, I gave the Hewling term, which is also vacuum polarization. But to actually compute what happens in the process that I mentioned, which is E plus E minus to mu plus mu minus. Okay. Delta. So this splitting is only for the L equals 0 state. Yeah. So yeah, that's all it is. Okay. Questions? Questions? Everything's crystal clear? Okay, good. Yes. The formula is for the potential for the CC bar system. Okay. So it's a quantum non-relativistic quantum mechanical model where you solve this potential, you get the energy levels and so on. No, this string has nothing to do with that string theory. So this is QCD strings. In fact, that so-called string theory, it was born here from various scattering things. So, and why is it string? Because, good question. So you have two possibilities. If you have CC bar sitting over here statically, then you have, let's say, the chromomagnetic lines, that they can be like this, like this. So this will be Coulombic, right? Or you can have the situation where a line comes, but it's actually attracted and comes back here, comes attracted like here. So this is confining. So this is called a QCD flux tube. Flux of what? Chromomagnetic lines. Okay. So it's a chromomagnetic field which behaves like this. Obviously, these are all heuristic pictures. But for instance, you can solve QCD on the lattice on the computer. You can take the field equations and try to solve them. And then you can ask very specific questions of what kind of behaviors are these two static objects experiencing. And then you can characterize them and see signals for whether it is a string-like behavior or not. So these lattice people also do all these things, and then they can see. Okay, so it's the 1 by r like behavior that actually allows you separation of coordinates and all. But even this, if it's just an r potential, it is still, as far as I can see, it still has spherical symmetry. Okay, I don't know the exact answer. I mean, this is a picture, so it seems like you have lost cylindrical, the full. So I don't know. In any case, the hydrogenic or positonium-like behavior is valid only for low-lying states. As you go higher up, of course, it comes apart. So you have to study these models to see exactly what is meant by these things. In Griffiths already has a pretty decent description you can have. So Griffiths always gives a rather nice description, but of course, if you're a more advanced student, it will not satisfy you. So that will impel you to look for more detailed references to study the topic. Yeah. Anything else? More questions? Mr. Kundu, any more questions? Yeah. Crystal clear. Obvious. Yeah. Is okay? Is all right? Any more questions? Okay, good. Yeah. Okay, so sorry about robbing you of 20 minutes of class time, but I can't really proceed today.